But first, here is this awesome photo. Let's call it Crocs taking a nip of hippo or natural recycling. Isn't it awesome? Think about how big the hippo is, and then you will freak out when you realize how enormous the crocodiles are. Okay, here's the question, number 3, the modeling question for the small intestine design. Now, the first part of the question, A, is to calculate the overall energy density of the food, assuming that we have to satisfy a DMR of 530 kilojoules per day. And we're assuming that the nutrient composition of the food, which is rabbits, is 23% protein, 11% fat, 0 carbs, 10% indigestibles, and 56% water. These are just made up numbers, so you would actually have to look up values for your animal design. Okay, but the first part of the question is, what is the overall energy density of the food? Now, if you have trouble imagining what this means, think about it as the DMR is like the bucket that we're trying to fill. Think of it as your hunger, how hungry you are, okay? And you're going to fill that up. Oh, and this is going to be in kilojoules, right? 530 kilojoules. And to fill that up, we have food, which has a particular value of kilojoules. So the question becomes, how many units of that food do we have to eat? And the energy density is basically how many kilojoules per gram, right? And so you can figure out what the value of the rabbit is in kilojoules because you know the percent composition. So it's proteins, which is 23%, fats, which is 11%, carbs, which is 0%, indigestible, 10%, and water, 56%. Each of these has an energy value or an energy density. And so proteins for a snake is going to be 18.15 kilojoules per gram. Fat, 39.2. Carbs is 15.9. Indigestible, 0. And water is 0. Okay, so that is going to mean that, like, 23% of the rabbit is protein, and then like another, let's say 11% is going to be fat. And those are the only portions that's going to contribute to the caloric or kilojoule content of the rabbit. But the overall value of the rabbit is an average over the entire animal, right? Because you're eating units of rabbit. You're not just sucking out the proteins and the fats, right? So the question becomes, what is the value of one of the rabbit per gram? Let's start with that part. So to calculate that, the energy density of the rabbit is just a weighted average of the percent nutrient composition times the energy density of that nutrient for each one added together. So this part is going to be the protein. This part is the fat. This part is the carb, the indigestible, and the water. Sum that all up, all of these percentages should add up to 100% of the food. Okay, So this 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 is the amount for proteins. This is the amount for fats, and then these, of course, all contribute 0, 0, 0. So that means that the rabbit per gram is worth 8.49 about kilojoules. So 8.49 kilojoules per gram. Okay, that's part A. Part B, okay, so assume that the snake is eating enough to support its metabolic rate each day. Okay, so what is the mass of food per day that the snake must assimilate to support its metabolic rate? Okay, so it's just asking you how many grams of this food do you need to fill up this bucket? Okay, so B, okay, so mass of food is then just going to be how big is your bucket, the DMR, divided by the energy density of the food, right? How much you need divided by the value. So that's 530 kilojoules divided by 8.4865 kilojoules per gram. And that comes out to be 62.452 grams per day. Easy. Okay, so now if you want to convert to kilograms per day, you just divide by 1,000, right? So 1 kilogram divided by 1,000 grams. So that comes out to be 0.0624. That's enough kilograms per day. Okay, assume an assimilation efficiency of 90%. So that means that 90% of the food is converted into usable energy, and what of the amount that you consume, 10% is lost to heat and other waste. So the snake will need to consume 0.0624 kilograms per day divided by 0.9. That's going to be 0.0657 kilograms per day consumed. So he needs to eat a little bit more. Part 3D, how many grams of each component would have to be assimilated per day? So we go back to the amount that's assimilated, which is this. This is the assimilated, right? So if we go with the gram amount, okay, so there's so the food is so for protein is going to be, it's 23% protein, so 0.23% protein times the amount of food, 0.06, oops, sorry, 62.452 grams per day. So 23% of that is protein. So that's going to be 14.364 grams per day protein. And fat, same thing, 0.1111% times the food. Okay, that's going to be 6.870 grams per day fat. So to get the molar amount, you just have to divide the grams by the molecular weight. So protein moles is going to be 14.364 grams per day divided by the molecular weight, which is 135 grams per mole. Okay, so that's 0.1064 moles per day for the protein, and for fat, 6.870 grams per day over the molecular weight, which is 256. So that's 0.0268 moles per day. Okay, so this snake is eating mostly protein, and and proteins require a transporter. So that's what's going to is going to be the rate limiting step for absorption. Okay, so we're going to select the proline uptake rate of an iguana because it's also a reptile, and we have a rate for that from Withers. It's so the proline absorption rate is 271 nanomoles per minute centimeters squared at 37 degrees Celsius. That's the rate that it's given to us in. But our snake is at a TB of 25, so need to Q10 correct. So we take our rate of 271 and use Q10 of 2.5 and correct. So 25 minus 37 over 10. Okay, so that's going to be 271 times 2.5 to the minus 1.2, which is going to come out to be 90.25 nanomoles per minute centimeters squared. Then we have to convert units. So this is going to be 90.25, and nanomoles is 10 to the minus 9 moles. And we're working in per day, so we need to convert per minute to per day. So there's 60 minutes in an hour, and there's 24 hours per day. So that should cancel out our units and multiply through, and we get 12,960 10 to the minus 9 moles per day centimeters squared. And so then if we just, let's see, how many can we take off of this minus 9? 1, 2, 3, 4, 5. So we can take off 5. So if it's 1.2996 times 10 to the minus 4 moles per day centimeters squared. And that's our transporter rate. Okay, add another page. Okay, and keep going. The next part is calculate the nominal surface area required to absorb enough amino acids per day to support the metabolic rate. Okay, so this is going to be like how many moles needed to transport. Divided by, this is like what we need to get done. And then this is the rate of transport. This is how fast we can do it. And this is per centimeter squared. And that will tell us how many centimeters squared we need to get it done in a day. Oh, sorry, because this is per day as well. Okay, so the numerator is 0.106399 moles per day, because that's what we had up here. This is what we need to transport, this amount, and this is the rate per day that we can transport it in. Okay, so that's the task, and then this is what we need to get done per day, and then this is how fast we can do it per day per square centimeter. So we just have to figure out how many square centimeters we need. Okay, so these units will oops, geez, how did that happen? Okay, this will cancel, and what we end up with is 818.713 centimeters squared. So this is the surface area required sorry about that. To transport in a day. Okay. So if we assume that the intestine has an inner diameter of 5 centimeters and an outer diameter of 7 centimeters, so that means that it's like this. Okay, and so this inner diameter is 5 and the outer diameter is 7. Calculate the length of the intestine in meters that we need for this surface area. Okay, so surface area is, we're going to use the formula for a cylinder, and that's just so the cylinder. So we're thinking of this cylinder as a rectangle. Like if we take this and cut it and then open it up, what we have is the length of the gut, and then the width is just this circumference. So this circumference is just pi d, right? Circumference of a circle. And so then it just becomes, do we use the inner diameter or the outer diameter? And since the absorptive surface is on the inner diameter, we're going to use the inner diameter. Okay, so surface area equals pi times d times L. So that's 818.713 centimeters squared equals pi times 5 centimeters times L. So we just solve for L, and we divide 818 by pi times 5, and we get the answer 52.12088 centimeters. That's pretty short. It's a half a centimeter. It's not reasonable for a 15-meter snake to have a half a meter gut. Seems too short. Okay, so in fact, we find out that they don't eat every day. They actually eat a large meal, enough for 60 days, and digest it over 7 days. Okay, so if that's the case, we're going to redesign the food. We're going to redesign the gut to take account of their actual feeding pattern. So the mass of the food mass of 60 days worth of food. Okay, so we just go back to the amount that we need to assimilate per day, which is here, and multiply that by 60. Okay, so 0.6 0.06245 kilograms per day times 60 days equals 3.747 kilograms per feeding. Okay, how many rabbits? Well, if one rabbit is about 1 kilogram, which is about 2.2 pounds, that seems reasonable, then this is about 3 to 4 rabbits. Some of you guys said 100 grams. Like, I don't know if your rabbits are fetal rabbits, but that's a really small rabbit. Okay. Now we're going to recalculate the intestinal model to absorb this food over 7 days. Okay, so the amount of protein per meal is again just 23%, because that's the food concentration, times 3.747 kilograms per feeding. And that is going to give us 0.861 kilograms of protein per feeding, or 861 grams. So if we assimilate this over 7 days, then the per day assimilation rate is going to be just 861 grams divided by 7 days, and that is going to be 123.12 grams per day. Okay, so again, we just convert to moles. Okay, and that's 123.12 grams per day divided by 135 grams per mole, divided by the molecular weight, and that's going to give us 0.911, let's just say 12 moles per day. Surface area required is then we can just use the same transporter rate. So 0.912 moles per day divided by 1.2996 times 10 to the minus 4 moles per day centimeters squared. And again, this will cancel, and we get 7,017.54 centimeters squared. So the length of intestine is just 7017.54 centimeters squared divided by pi times 5 centimeters, pi d, and that's going to give us 446.75 centimeters, or 4.47 meters. And so that seems much more reasonable and comes out to approximately 2/3 its length. 2/3 times 5 meters is about 3.33 meters. So this is much closer. Yeah, and that's the end of the problem. If you wanted to figure out the volume that the gut occupied, that would be when you would use the outer diameter for this question. Okay, so the key to this question is to understand just what are the quantities that you're estimating. Make sure that you understand what you're trying to solve for in terms of the problem, and it should be pretty straightforward. Just trust what you know. Okay, thank you. Bye.